Welcome to today's webinar with Daniel Lee, which I'm very excited about for multiple reasons. The first reason is that, like almost everyone else, I have been blown away by the capabilities of large language models like GPT. But if I'm being totally honest, the success of that also made me somewhat insecure. Like, will there still be a place for Bayesian modeling with all that hyper AI? I personally think the answer is yes, but I also got really curious when Daniel told me that he built a GPT in a probabilistic programming language. The other reason, though, why I'm very excited to have Daniel here today is that he actually has been very inspirational for me. In 2016, Daniel co-founded a Bayesian startup called Generative. And for me, that was the first time that I was aware of that someone actually started a company around Bayesian modeling. And I remember being extremely excited about that because while I already loved Bayesian statistics back then, I didn't know that it was established enough to actually build a company around. So seeing this was really the first time where I considered building a Bayesian company myself. So Daniel, welcome to the webinar and thanks for being an early inspiration for PyMC Labs.
Hey, Thomas, thank you. I hate to break it to you, but back then we tried to start a company going horizontal and taking stand to the masses, and we found out there weren't enough customers. So you're in a better situation now than we were in 2016, 2017.
Well, maybe you opened the market and now we're reaping the benefits.
Yeah.
So I'd like to start off by hearing a bit about your origin story, how you got involved with Stan, maybe, and of course, maybe also around that startup in the Bayesian space.
Yeah, it's actually kind of funny. I was working for Andrew Gelman before Stan started. I was working for Andrew Gelman starting 2009. This was before Matt Hoffman and Bob Carpenter joined the group. But my Bayesian spin actually started a little before that. I mean, yeah, I went to grad school at Cambridge, University of Cambridge, and I took a bunch of stats courses, mostly because I didn't know how to do anything else. Um, I didn't know anything about stats. I'm talking about I didn't know what a normal distribution was before 2008. So I'm at Cambridge, do a bunch of stats, take some of the Bayesian statistics courses, and David Spiegelhalter just returned back to the department. And so he's teaching us how to use wind bugs for his applied Bayesian course. Of course, given what Cambridge is, the actual test itself was done on pencil and paper, proving convergence proofs of give sampler instead of anything computer related. But even before that, I guess during Cambridge, I was working also on causality and graphical models and causality. So by the time I got through that program, I had some idea of how bugs worked, like fundamentally. You build a graph, you do all this mapping of the graph and figuring out how the nodes can break apart to do this conjugate stuff. And I really wanted to work on bugs. And at that point, David Spiegelhalter told me that bugs was dead. This was 2009. And he was right. I think people stopped working on the code roughly in 92 or maybe even a few years after that. A few bug patches here and there. So when Bob and Matt showed up and they started building up Stan, which wasn't called Stan at that point yet, I was able to really understand what all the pieces were and figure out that we're doing something similar yet not the same. We were building out this expression graph that allows for loops and functions, which is great. And that just kind of kicked in.
Really cool, yeah. And I mean, of course, Stan has also been very inspirational for PyMC in many of the design choices. And I actually remember that in 2015, you had reached out to me and some other PyMC developers about the ADVI paper, something which we then also subsequently implemented in PyMC. So from there, I guess, to today, how did you get interested in GPTs and I guess come to view this through your Bayesian lens, I guess?
Yeah. So after the start of Generable, I left at the end of 2021, and I was looking at different opportunities. At that point, I was consulting a bit. But one of the opportunities that came across my lap was something in the deep learning space. And I really decided to dig in to try to see if that was something for me. And once I started digging, I needed to keep going. So I just needed to find out what the model was. I couldn't try to really look at an opportunity unless I understood what was going on. And I figured, given my background, I'd work on the computational side. I wouldn't work on just applying neural nets to some problem. I figured I'd be working deeper. So that's how it came about. It ended up I didn't go there. I ended up at a sports analytics company instead, where we do a lot of Bayesian modeling. But I still have this knowledge, and I think it's really neat to look at these models.
So my curiosity is definitely piqued. So yeah, you have some slides to really go into the depth of GPTs and how you can take a probabilistic perspective on those. So yeah, looking forward to hearing about that. And for anyone in the audience, thanks for joining. You can ask questions, which we'll get to at the end of the presentation by posting them at the Q&A bottom, and then they will just show up there and we'll get to them later.
Sounds good. Let me know if you see the slides. Yep, it looks like it's active. Cool. All right. Hello, everybody. By the way, it's still weird getting over this virtual talking to people without seeing any reaction, but we'll try this. This talk is about GPTs and probabilistic programming, and there's a subtitle here. I want to really get at separating inference from model, but we won't touch that till the very end. Some notes before I start. Lots of credit is due. This is not all work that I did. So the references are on the last slide. There are tons that I left out. Yeah, you can dig into this stuff for a while. All the mistakes you see here are mine. And please, after this talk, if you think you can build a production level GPT in a PPL, that's not what I'm encouraging, but it is a very good pedagogical exercise. I have to apologize. This talk is going to be a little bit weirdly highly technical and highly non-technical at the same time. So hopefully you can keep up. Hopefully there's something for everybody here. We'll start out with what the problem is that we're trying to solve, because I think that's always a good place to start. This is how I'm characterizing it. Given some text, we want new text that's a continuation of the text that's given. We can start with an example. If we put in, oh, Romeo, Romeo, wherefore art, hopefully we can kind of expect the output to be thou Romeo. So that's a continuation of the text. But really, when you get down to it, we're looking for something plausible. We're not looking for the actual continuation of the text. This is why GPTs can hallucinate. This is why GPTs can, all these large language models have some sort of uncertainty in them. We're not exactly sure what should come next, but we want something plausible. All right, so let's talk about one of these models inside this class of large language models, something to do this task. And it's called a generative pre-trained transformer. The generative part is that the model is capable of generating text or images or whatever you're interested in. But in our case, it's going to be text. Pre-trained means that the model is trained on a data set before use. And this is usually a large data set. And pre-trained means that you take the parameters of interest and you stash them somewhere and you're able to use them later. The transformer, this is the interesting part, and hopefully we'll get to dig into this a little bit today, is that the model uses this parallel multi-headed attention mechanism. And this is from the attention is all you need paper, the thing that really sets off what a transformer is and has made a large breakthrough in neural net architectures. So that's what a GPT is. I'm going to walk through building a GPT in Stan, and I'm going to try to go through this as fast as I can. So we're going to cover a Bigram model, which is a simple model that isn't a GPT. We're going to build on top of that, go through a few iterations. We'll get to self-attention and multi-headed self-attention. We're going to skip sort of the more neural networky things that you need, but for the interest of time, it's less important for understanding what self-attention and multi-headed self-attention is. Just to let you know, there is a repo for this. This is code, it works. But once again, all the mistakes are mine. All right, so before we actually build the first model here, the data, we're going to start with data. You can find a subset of Shakespeare data from Andre Karpathy's repo here. And some of the examples, the start, I believe these are the first 100 lines, looks like this for Citizen. Before we proceed any further, it includes tokens like new line, spaces, period, colon. So these things are all here. Here's another example, just picking some other random spot in the text. So that's what we have. We're trying to build, that's our data. And we're going to try to build something that sort of sounds like this. So what we do with the data is we first convert it to a sequence. We take the sequence of text and we convert it to a sequence of numbers. And here there are 65 characters. You might think the English language is 26 characters. Why are there 65? It's 26 for the characters, lowercase, 26 for uppercase, and then you got special characters there. For example, for the first 10 characters, first sit now gets mapped in. And what we have here is that we're going to structure the data to be passed into this PPL, into these models as batch size and block size. Batch size is the number of replicates of data. So number of rows of data, sorry, not replicates, rows of data. Block size is how much context you have when you're looking at this. So how this works, X is the data and Y is the correct answer. If you look at the first character, 26, you're going to expect the next character to be 40. And you can see that 40 is here, right? You can see this is all shifted by one. So if you look at 26 and 40, the next character out is going to be 50. And you can go all the way to the full size, the block size. So if you have this whole vector of input, you'd expect that to be your output. This is written in Stan. So in Stan, we define data up ahead. This is slightly different than PyMC. But what you have is the vocab size. Here is 65. Batch size is 32. Block size is 8. We can change this to larger numbers, and that will mean that you have more data and more context to look at. But that's what we're starting with. In this example, we're not going to talk about a validation set. We're going to use a training set, but the code itself has training and validation split out. The max tokens is the number of tokens to generate from this model. So here's XB. Once again, that's batch size, the number of rows of data, and block size is the context length. And each of those has to be between 1 and the number 65. All right, so the first model is a Bigram model, which is only looking at the last to predict the next. So what that looks like is we have this parameter token embedding. So this is the parameter. We have vocab size. So that's 65 slots where we have a vector of size 65. And that's our parameters. And what ends up happening is that we take a look at the next character, YB, and then we take the XP of that thing and we look at what the token embedding is for that position. So this gives us a number of 1 to 65, and that will give us a vector of 65, and we'll pass it into a categorical logit. If you look at this whole block encodes what the neural net deep learning literature calls cross entropy loss or log loss. So that's what this is encoding. If you look at it as a statistical model, this is a categorical logit of YB of this index coming from this vector here. Okay, so that's a simple Bigram model. What we can do next is we're going to go and change the embedding size. So we're going to change the embedding size to 32, for example. So we're going to add a new data variable and embed. And we're going to add a few more parameters here. So instead of this being a 65 vocab size by 65 token embedding, now it's 65 by 32. It's a little smaller here, but what we have is we have what they call a language modeling head, and there's a matrix that multiplies it and then an offset. So if you look at the math of this, it's just like a linear model here. You've got a 32 vector and you actually want a 65 out. So you got 32, this token embedding X is size 32. So we're going to do vocab size times that embed. So that's going to turn it back to vocab size. And then we're going to add the vocab size. If you look at the transform parameters block again, we're going to once again have this categorical logit here with this used to just be the token embedding XB here. But now we're going to replace that with, we're going to run this through the language modeling head with these variables, and that's going to turn our smaller size and embed into this bigger size vocab size, but it's going to include this other mixing up of all the parameters. So that's the second stage of this building up into a GPT model.
So you're not placing any priors here, right? These are just
no
valued parameters.
No, and that's a great question, Thomas. We're not going to actually be putting any priors on this model itself. This model is the statistical model that is described by some of the tutorials. In particular, this one, I'll point to the one, is under Karpathy's Let's Build a GPT in Code Spelled Out tutorial. And yeah, we can probably put priors on it and do something really clever, but in this case, we're not doing anything here. All right, so the next thing, what do you do with this? This still doesn't look back at anything, right? It's just using that last character to tell you what's going on to the next character. It has some of this mixing up of variables. It's if you look at the number of parameters now, we've got a lot of them. There's 4,000 change here now already off of this model. Okay, so now we start using position. So here we've added a new parameter, position embedding. So it's block size. Once again, this is the number of characters, columns of data that we're looking at. And it's of size and embed. And what this is that for each of the positions, we have a different weighting of the token embedding. So this will tell you if the letter I ends up in the first position or the second position or the third position, it might have a different weight here. And that's what it's doing. To use it, we just add it to the token embedding at that position. And then we go through the same exercise here. But now this XB is now using the position embedding. So that's what ends up happening. We pass it through the same language modeling head. Then we get out our logits and we pass that through our logits. Once again, we're not actually using a lot of the past history here. We're just using the position of that last character as input. Okay. On to the really fun stuff, the meat of the conversation here today. So this is self-attention. What we're going to introduce here are new values, new parameters here, and they're going to be key, query, and value. They're going to be n embed by n embed, each of them, so they're matrices. So once again, they're called key, query, and value. And how it's used is through a function. We're just going to call x. We're going to pass in it to a function called self-attention. We're going to do key, query, value. And we'll dig into what that does. But these are the new parameters that get introduced. Before we get into what the implementation looks like, let's just walk through a quick example to get sort of a intuitive sense of what this is. So the animal didn't cross the street because it was too tired. And that might be the query, or sorry, that might be this is the example. The query, we might be interested in this word it. What does the word it relate to, right? The animal didn't cross the street because it was too tired. Is it the animal? Is it street? Is it something else? And so the query is this it. The key is roughly what it's gonna refer to. So that's essentially what we're trying to do. We're going to try to mix those up a bit and then get something reasonable out. So here we go. This is the function self-attention. Once again, we're passing it this x. This x is batch size by block size, and it's an embed, but we're passing it the x, key, query, and value. Okay. It comes in, we convert it to a matrix. This is all stand code, which isn't really relevant here, but we're going to use the key, query, and value here. We're going to take this key, we're going to multiply by the X matrix. We're going to take the query, we're going to multiply it by the X matrix, and we're going to take the value and also multiply it by the X matrix. What we're going to do is take that query and take that key, and we're going to do something called a scaled dot product self-attention. So that's multiplying those two things together. If you think of these as two single vectors, we're going to get a single number out of it, right? So if we take this vector and that vector and we multiply it, we'll get a single number where this is related to something on this side. And when those two things are related, they'll be high, and when it's less related, it'll be low. And we get out this, we divide by the square root of head size, and this is to control for the variance in the softmax here. So this is a computational necessity here, but the key is that we have this query, we have this key, right? And then we got what you're looking at, the word it, and what does that refer to? And that's going to give you this block matrix, this square matrix. And then for this type of work, we're going to use something called encoder, which ends up mapping this to a lower triangular matrix. And that's what this step is. So for each row, we're just going to take the lower triangular and make it so that it's a softmax, so that it all sums to 1 for that lower triangular row, each row. All right. Now the output itself is you take that weighted thing and multiply it by our value. And that ends up being reshaped and then passed out as our output. And it looks just like our original X. So this X is array, batch size, block size, and embed. And this thing ends up being batch size, block size, and embed. And then we, once again, pass it through the same mechanism. We pass it through the language modeling head and go compute the loss the exact same way. So this is the self-attention. So once again, it's this idea of this query and this key. What does it relate to? What does it relate to? And it relates to here the animal, mostly. Okay. So now, getting into multi-headed self-attention. It's not actually that complicated once you get this far. So we end up with multiple self-attention parameters. Instead of a single self-attention block, we end up with, we end up with n head. So we have multiple ones of these. Sorry, it's moving without me wanted to. Okay. Once again, they're key query value, but we just have n head of them. So we're repeating it. Once again, multi-headed. We go through the same exercise here and then just pass it through this multi-head self-attention. Now, what's different about this is that the example, if we looked at the example, the animal didn't cross the street because it was too tired. Each of these are now different queries. So different keys. This is a single query. When we do this, we have multiple queries and multiple keys, but here we have a single query. We're going to visualize it with multiple keys. So in this one thing here, we'll take the orange one. It was related to the animal mostly. Here, it is related to it. This one thinks it's it or didn't. And if we look at it here, it thinks it's, let's see, cross. So we have multiple keys here and a single query, and then we can do this for every single one of these on the right side as well. So we're going to do the same self-attention thing here, except now we've got a different head size instead of an embed. We've got something that's smaller, or it might be the same size, and we've got a bigger embedding size. And what we end up doing is we repeat the self-attention multiple times, and we're just going to concatenate the results. So the first head size elements are going to be from the self-attention the first time. The second head size elements are going to be the second self-attention block, third, fourth, fifth, so on. Okay, so that's really the multi-headed self-attention here. We've covered so far, I know it's been very, very brief, but we've covered this part of the architecture right here. There's more to make this work, and we're going to skip it for now. If you want, you can go to this repo. I'll send out the slides, and you'll have access to it. But there's also this adding a feed forward layer, and working in skip connections, which are computational tricks, larger feed forward networks, and then adding blocks and dropout. Okay. So getting back to the talk itself, so we've built out this GPT, we have it. What I want to note is that there's a statistical model underneath this all. And I'm going to define a statistical model as here's data X, and this X is multi-dimensional. It can be all sorts of weird shapes. Their parameters theta, these are the things that we want to estimate, also multi-dimensional. And we're going to link the two with the statistical model, P of theta comma X. And here we can think of the P being this particular GPT. If you change one of the layers, it'll be a different P, right? So here, the way I've defined it, P of theta X is a function. So given my theta, given my X, it returns a single number. Mathematical notation, if theta is in Rn and X is in Rm, then we take Rn plus M, and then we get out a positive real, which includes 0. This model, the statistical model, links our data and parameters. And what we want to do in setting up this statistical model is higher is better, right? So here we want the log loss to be lower. And so that's why we have the categorical logit. there. Something to note here is that we've written out the statistical model, but what we have here is that the inference is the statistical inference for fitting these models is separate. So given the statistical model that we have, I think that there are three types of inference, and people may disagree with me, and this is a bit of my opinion here, but I do think things break down into three principal types of statistical inference with different goals. There are tons of other ad hoc methods that work. I'll put a star next to that. Work meaning it tries to achieve a goal, but not necessarily something that's as clean as optimization. What we're trying to do is find the set of parameters that give the highest value. So if we talk about approximate inference, we're going to say the problem that I have is really hard. I can pick an easier problem to solve, something with really good properties. I'm going to find the parameters of that easier problem that give me the best answer. And the third type of inference is Bayesian inference. And the goal of Bayesian inference is to find the distribution of parameters that makes sense given the data that you've seen. To be a little more mathematical about it, what we've got here is that given this P of theta X, right, this model, given your parameters and your data, what we're trying to find is this theta hat, the best values of your parameters, which is going to maximize this. So, right now we're going to deal with X being static, like it's not moving. So all we're going to try to do is search over the space of thetas and try to find this theta hat. We have approximate inference, and here is this example is ADVI. There are other different algorithms for approximate inference, including EM, EP, and what we're trying to do in ADVI is we're going to approximate the Bayesian posterior distribution, the probability of theta given X. So this is a distribution over theta. We're going to approximate that with some Q, some other function where their parameters phi. And phi, we're going to set phi hat, the best values of phi hat as arg min over phi, where the KL divergence between Q and P of theta X is minimized. So that's really, this Q and P are really close. We're going to try to find the phi that makes it really close. And we're going to take that phi, pass it into Q, and use that as my approximate distribution for P. And then Bayesian inference, we've got, this is MCMC, we've got P, we want P of the probability of the parameters itself, given the data that we've seen. And we're going to approximate this with the sequence of theta 1, theta 2, all the way to theta n. So we're going to use that as a proxy for what we have as our distribution. So getting back to what we're talking about with GPTs, the inference on GPTs, we're going to use a stochastic optimization algorithm. In the example that I've shown in code in Stan, what I ended up doing was using a stochastic LBFGS, but in reality, we should be using something like Atom. The idea of stochastic optimization is you break the data into small chunks. Using each of the small chunks, you update a subset of parameters in your P. You're going to keep doing this again and again until you're satisfied. And why would you do this? Why would you break it into small chunks? The first issue is a practical concern. Oftentimes, the data that we want to fit is too large to fit all at once, so it would take too long. So we break it into smaller chunks, pass it into this optimization procedure, go a little bit, and then replace that data with a different set of data that's going to update a different set of parameters. We're going to keep going and going. I'm going to wrap up my talk really with when to use and when not to use these three different techniques. And these are really opinions. Feel free to ask questions or disagree with me. That's absolutely fine. For optimization, I tend to think that you want to use optimization most often, and you want to use this when you want usable estimates, but you don't really care about the uncertainty of the estimates. And the other thing is for speed purposes. I think that you should stop using it when you're not converging to a solution. That indicates that your algorithm is not suited to the problem that you're solving, so the optima that you're getting is not actually the principled optima that you're looking for. The other thing that you don't want to use it for are hierarchical models, typically. Just a fun thing to try at home, try optimizing the 8 schools example, and you'll find that the variance component, the hyperparameter, the hypervariance component is going to want to go to 0. And there's a reason for that. The optima actually happens when it violates some of the modeling assumptions that you make. So that's when I wouldn't use it. If we talk about full Bayesian inference, we're going to use it when parameter inference and uncertainty are very important, or when you want to do complex models and you don't know how this plays out. So you do want something that will try to capture that. When I wouldn't use it are when speed are very important, and when we have a multimodal posterior, something like a GPT. You really shouldn't be trying to fit a GPT with Bayesian inference, because you're not going to achieve the goal of getting a parameter distribution for all the weights. It's not possible. Approximate inference, I'd use it for complex models when you don't need the true uncertainty, when you can use an approximation to that. And I wouldn't actually use it when I need the uncertainty, but I don't know how good the approximate algorithm is relative to my actual process, my actual problem. That happens a lot of times, but not all the time. Sometimes you do know how good your approximation is. The takeaways here: 1, GPT can be written in a PPL if you want. The statistical model can be written in a PPL. 2, you can separate out statistical models from the inference. This will give you a chance to look at what the statistical model is doing. And 3, I would think about choosing inference techniques wisely. References, the first one, if you haven't seen this yet, Let's Build GPT from Scratch and Code Spelled Out. That's what most of this work is based off of. Here's the Original Attention is All You Need paper. This blog post helped me understand what the key and query and values actually mean. This is a GitHub repo with code for the tutorial. And if you're interested in Stan, that's what this is based on. That's the GitHub repo for Stan. Thank you all.
Thank you so much. That was really, really interesting. I'm going to start with a question from the audience, and then I also have some questions. Dustin asks, I think, about an earlier thing in the talk, what the query would map it to in the sentence that you presented. The animal didn't cross the road because it was raining.
Interesting. So so we get to dive into something that I've been thinking a lot about all right, hang on 1 second. Okay. So as a concept, this is what we're trying to get across, is queries and keys. We've written it out in the statistical model, but it turns out that there's no reason why the keys and queries aren't flopped. There's no reason that this actually does what we think it does. We're just finding parameter values that, well, when I looked at it this way, it sure looks like it is related to the animal. But in reality, especially when we're doing this character by character, it's not really giving us something interpretable. I don't know if that answered the question, but that I've been thinking about that a lot and realizing that without the use of priors, these things are just like what I don't quite understand how these things all tie together in such a way that we get good output, yet at the same time we do. So obviously inference is working. Not sure exactly why.
Another question, how do you know the approximate inference algorithm is good and matches reality?
That's tough. The place I would go to is Tamara Broderick and her collaborators. Tamara Broderick's at MIT, and her collaborators have been trying to quantify this a lot. There's a lot of research. If you look through her papers, she'll reference a bunch, but there are a lot of papers that talk about this, and she's one of the ones that are really trying to quantify when that happens. I know a little bit about ADVI. I don't know too much about the others, but really, ADVI really approximates the posterior well when the posterior looks on the unconstrained scale like a multivariate normal. When it's a multivariate normal, you're going to be able to sample MCMC really well. So it's like a trade-off here. It's you're those two things happen when they're good, and also if it's not a hierarchical model, you should be able to optimize it and get close to the same answer. So I don't know. I think it has to be done pragmatically, as Thomas alluded to. I was thinking about talking about iterating over models and how to really put things into production. I think this is a production ad hoc type of, you got to try it and figure it out. That's the best advice I have.
Cool. Kieran Gautier asks, hi Dan, great talk. Wondering if you could speak more to the batching of the data when using LBFGS. How small are you making it? And what's the rationale based on the iterative parameter updating? Seems like that would be a real challenge to get to work properly and quickly at the same time.
Yeah, I didn't show any output here. I realize that now, but it doesn't look great. The problem here is that I don't think batching with LBFGS is ever going to take you to the right spot. So I think anyone trying this should look at Atom, should look at some of the other techniques, and yeah, I think that you're asking very hard questions, and I've got no good answers here.
All right. So I guess in that vein of asking hard questions, I think that perspective of separating model from inference is a useful one, and definitely I think one where there often can be a lot of interesting connections between machine learning and Bayesian modeling. And I think there's been a lot of great work on trying to link the two. If you do logistic regression, you place normal priors, you can just write that differently and have logistic regression with a quadratic loss, which is what machine learners have been doing a lot. So there are these deep connections between priors and regularization. And that extends to neural networks and has been really at the core of Bayesian neural networks and that. So, I mean, your work seems to squarely fit within that whole endeavor, I guess, once you would add priors. So I'm curious, what do you think? Well, as a first question, what do you think there's anything applicable in terms of like separating these two out that allows us to understand or build?
Yeah, I can always talk about personal. For me personally, the benefit of separating out the two was that digging into GPTs and looking at this, I've learned a few techniques that I wouldn't have gone to if I stayed in my Bayesian lane and just try to model fundamentally. For example, the key query concept and just picking up on internal representations using the same data and like just doing this type of trick, I think I can apply it somewhere else, right? And does it make sense as a statistical model? No, because I still don't know what this, I know I want to interpret it as like, I got this query on this side, I got these keys on the other side. But if I think about the stats of it and the math of it, there's no reason why this should do what I want it to do. So if I was to try to do that from scratch, I would actually be putting in priors, I would put in more structure to do that. But that may be limiting in the modeling side. And, for me, like I said, looking at it this way, I take a look and I'm like, hey, that's cool. I should probably try to think outside the box a little bit. On the flip side, it's like thinking about the inference side, you're going to try to optimize this thing, and it's not going to get you to something that you really truly believe is an optima, because you kind of understand when you look at this enough, you have to understand that this is going to be super multimodal. So the key quantity of interest here is the prediction. And so you can toss away some of these things that I deeply care about through parameter inference. So both sides, like something to learn here for me.
Mm. Yeah, and I mean, I guess that does fit within what I was saying is there's definitely some understanding, I think, being provided by understanding that like, well, this type of regularization really is just a prior. And I wonder if just by keeping on pulling at that thread and applying that same reasoning to the key value lookup, that maybe some understanding can be gained as well, because I actually would assume that this confusion about like, well, why does that even work? Putting it together like that is not just like something that the two of us are not fully on board with, but actually I think no one really knows, right? So, and I mean, this has been true, I guess, in machine learning a lot, where it's much more about, well, what works and why it works, or what it actually is doing is difficult to say. Yeah, so from that perspective, I think it could be a really interesting step in figuring that out. And yeah, I mean, maybe placing priors is one of those where we can also just get more interesting tools of regularization, like dropout, for example, right, can also be interpreted as a form of prior using a Bernoulli distribution. Of course, the other big thing with Bayesian modeling is uncertainty. And I mean, that also sounds like something that would be useful, and something that has been, I guess, criticized a lot with GPTs is that they tend to just do what's called hallucinations, right? So they provide the wrong answer and they don't really have that mechanism of saying, I don't know the answer to it. So do you think that that type of uncertainty that we're getting in the Bayesian framework, and obviously there would be some very hardcore approximation to be done, very likely we can really just run MC on this. But yeah, just like some form of Bayesian uncertainty in the predictions.
Well, I mean, I think for these sorts of models, I think we're talking about two different sorts of uncertainty here. One is, this hallucination is a property of the model, right? There's not enough structure in the model to help prevent that, and I hope people are working on it. I hope there's people really thinking about AI safety and changing the structure of the model to give it more context and more information that's not purely inside the training data, to tell it here's our rules that you should obey. That's essentially what a model is. But the parameter uncertainty of this, we're estimating a bunch of weights, and it's unclear to me yet how you would use that efficiently in such a large model, right? We're talking about 65 billion parameters. What am I going to do with replicates of 65 billion parameters, even 1,000 times? Like, what would I do with that where I have some sense of uncertainty of a weight in this one little thing, and right, even conditioning on you getting to one spot with 65 billion parameters, that's pretty good. You can always generate new text out of it. So even that has uncertainty. But when we start talking about the uncertainty of the estimation itself, I'm not exactly sure. I'm not an expert in that level of detail here. Like I said, I don't know what I would do with it. So that's my lack of imagination.
Yeah, it's true that a lot of the benefit in Bayesian modeling is only really realized to its fullest potential when we are building the type of models that we're usually building, where we really have an understanding of what each parameter means, right? But once that understanding goes away and we're in some 65 billion dimensional space, and we have no idea what those parameters actually relate to, what does even uncertainty mean in that space? Bruno has another question. Another potential issue is heteroscedasticity in the data. Grammar doesn't change over the years that swiftly, but other data sets are non-stationary.
True.
Yeah.
I don't know, how about this, Thomas? What would you do if you had heteroscedasticity in data? How would you approach it, right? And you've seen this GPT. Everything is exchangeable. Like there's nothing to tell you that anything's different. Is this how you would go and model a problem if a customer came to you?
Yeah. So we actually see that problem a lot, and I also had some fun exploring this in like just much simpler Bayesian neural networks. And I'll post a link to that blog post, but actually two of those things relate to this discussion. So one is these thoughts around priors and doing something more interesting. And well, one of the most interesting things we can do with Bayesian models is build hierarchical models. So I experimented around with a hierarchical neural network where it was like a very simple classification problem, just the two moons data set, finding like a separating hyperplane, but not just on one data set, but actually many data sets that was just like rotated. And then you fit one model to each of them and in a hierarchical way. So there's like basically sub networks that operate on each different data set. And that actually worked well, which was somewhat surprising because, like I said, like what even do these parameters mean, and what does that mean if we make them hierarchical? But they learned something useful, which they didn't learn in a non-hierarchical model.
Mm-hmm.
So that I thought was kind of cool, that there apparently are more structured priors that we can apply to this, and maybe that helps with these other more structural concerns you raised with, for example, the hallucination problem. The other one is around heteroscedasticity, is what if, for example, that classification problem is changing over time? So the best separating hyperplane is actually, so in that example, I'm rotating it just across the axis, and then placing a time varying parameter on the neural network weights. So rather than them just being constant across all that time, they're allowed to change. So and that also works. So what you get is like a time varying hyperplane that separates them at every time point. It's a different classifier essentially, but you still get this regularization through the Gaussian random walk prior that I applied there. So things can't just like change completely radically, but slowly over time. So yeah, like that is what I thought were like interesting combinations of these two. And I mean, I think like both of those probably could be applied really well to your GPT example, where instead of just one set of like, yeah, maybe you feed in some language from a very long time ago, and the same like also I guess language is not changing drastically, right? Like certain words are coming in and out of favor, certain grammatical things are changing, and I'm sure that that could be modeled in this by allowing the parameters to change over time. So yeah, that could be an interesting approach, I guess. And yeah, like then, and now we're talking about, of course, models, and then that's a totally different question what the inference would be. So yeah, I think it does make sense to treat those separate there.
Yeah, I mean, I think the takeaway here is that, you know, you and I probably would do the same thing, which is take a look at it and then decide we're going to try to build a better model, like use some knowledge that we have. Um, and that's for me at the scale of data that I work with. I think that's often the approach I will take. Almost all the time, I'll ask someone, some subject matter expert, and say, what thing do you know that I don't know? Can I incorporate that into the model, because that will help me get the output that I'm desiring. Right? When someone takes a look at some output and says this is good, that's bad, but the log loss doesn't change, we've left something off the table. So that's how I approach it.
Yeah, I agree. So we're almost at time, which is a bummer, but I just at in the last few minutes at least get your quick take on flipping this whole thing around, right? So now you talked about how we can, in a probabilistic programming framework, build GPTs, but you can also have GPTs write probabilistic programs, right? Like GPT-4 is very apt at building stand models, PyMC models. And one thing that I thought was kind of interesting is, can we use these frameworks for GPT to build internal representations, essentially, that allow it to causally reason about the world in a probabilistic way and answer like questions that require actual like causal Bayesian modeling to answer, and then like have the GPT build the Bayesian model to answer that question. I don't know, have you like played around with having it build stand models?
I've done a little bit, but I haven't done too much. Um, I know I've seen output that's absolutely mind blowing. Something that's trained on a few tokens at a time, figure out what the meaning of a question is. But one of the reasons I'm not using GPT so much, especially for writing statistical models, is that the hallucination thing is real for me, and it's telling me things that just don't work. It's really hard to tell whether or not some, like, once you get to a complicated process, it's I don't know, maybe I'll probably come to it soon, is my guess. I'm always a late adopter of tech, so um but really I've tried using it. I asked it to write some code for things that it knows a lot about, like Python, R code. It generates things that make sense. When I ask questions about models which don't exist yet, um, and it's starting to hallucinate things that seem plausible, and I could barely understand it. It's really hard for me to justify putting that into any sort of production use without digging into it. And where I'm at, I'm not trying to write boilerplate anymore. So if I was trying to write things that there are hundreds, thousands of examples for, and would just cut out time for me, yeah, absolutely, I would use it. But like I said, it's there. I'm looking for this time series model with these new components that no one's ever talked about except in this small room. And not that it's secret, it's just like no one's done it. So can GPT generate that for me? And when it can, like, great.
Yeah, I guess it's trained on plausibility. So something can look plausible but still be completely wrong. And that is pretty difficult to suss out, right? If you're not an expert who knows what the correct one would be, it's super easy to be fooled. So that definitely is a risk. So thanks so much for coming on. I definitely learned a lot about GPTs. I think for the participants, thanks for joining. If anyone is motivated to translate the examples from Stan to PyMC, I'd love to see that. So if you do that, please send me an email. We'll definitely put that on the blog. But yeah, thanks so much for coming on and teaching us about GPTs in probabilistic programming.